Okay, all right, so I put the slides on cue. Was everybody able to get them? That one of them? I'm going to go with that's a yes. No answer is a yes. Send me your email for some reason. Someone coming in?
Hear us? Anyone can?
Oh yeah, hey.
Okay, so it's good. Awesome. So microphone is this. Thank you. If you want to mute. Yeah, I think you used this before, right? Yeah, yeah. And use this.
Okay, is everyone ready? I'm going to get started. Okay, so, wow, we have a huge scope of stuff that I kind of hope to cover in the next 2 weeks. Looking back at what's been covered so far and what's in the future for the class, I made an impossible list of things I wanted to talk to you about. So I'm just going to talk about my favorite ones, and that's going to be the next 2 classes. So I think what Lana had originally put me down for was to talk about the role of fluids in brittle faulting, and zooming out a little bit from that and talking about more details about brittle faults, how they evolve, how we find them in the field, what they look like. And at every stage of the evolution of a brittle fault system, there's an important role for fluid-rock interactions. So I just picked this kind of fun news report after the Haida earthquake a couple years ago. There was sort of a temporary redistribution of the hot springs on the west coast of Vancouver Island. And this happened on faults, where the hot springs come up faults that were not the fault that slipped in the earthquake. There's all kinds of sets of active faults out there. Very few of them are mapped, but except by hot spring seekers. So the actual seismic potential or seismic history is essentially unknown, but the fluid flow regime in those faults were affected by a nearby earthquake on a different fault. So I have a little list of kind of causes and effects here, which is actually circular. I could have put it in a circle, but it fit better in a rectangle here. So anyway, faults, because rocks break in faults, that produces porosity. So faults are effectively the most permeable pathways through the brittle crust. So most of the upper crust, the permeability structure of the crust is controlled by the location, orientation, and the structural context of those faults. In turn, as fluids are moving through the faults, whether they be sourced from surrounding formations, even gases coming up from the mantle, or if they're actually produced by faulting, which I'll talk more about later, those fluids control the pressure in fault zones. So most of the time when we talk about stress on a fault, we're going to be talking about effective stress or shear stress, and those values are controlled by the balance between the tectonic load or the normal stress on the fault, which pushes inward on the fault, versus the pore pressure in the fault, which pushes outward against that. So the effective stress is the net stress on the fault when you can take the tectonic stress and subtract the pore pressure. And that's what controls whether the faults will actually rupture or not. The pressure in the fault zones, whether the fault is held at a stress that's near its failure threshold, controls the behavior of the fault on all scales. And I mean that in time and space. So it controls whether you might have a small earthquake or a large earthquake, what kind of size rupture you're looking at. It controls whether the fault will creep or trigger a larger fracture event. It also controls fault healing, because a lot of the fluid and rock interactions have to do with building new minerals, repairing damage that occurs during fracture events, or assisting with the deformation of minerals that are already present in the fault zone. So reconstructing so that a fault rock approaches back to the properties of a regular rock, a not deformed rock. The earthquake cycle then is controlling the fault valving, which we'll talk more about next week. But when a fault ruptures, that creates a new conduit, so facilitating more fluid flow. And then these fluid rock reactions that end up part of the rock record, so they record the history of rupture and healing on the fault surface. And one of the big growth areas in my field, in kind of brittle structural geology, is finding new ways to read that record and trying to understand how different slip events, different styles of slip are preserved by the minerals and the structures that are left behind because of this fluid rock interaction. So, okay, this is not a good start. I'm spending way too long on the first slide, but I only have 40 slides for today, so I promise we'll finish on time. Okay, I can hear nothing, so if anyone has any questions from one of the other schools, just like pipe up more loudly. Yeah, okay. Okay, so here's an overview of what I'm going to try to cover in the next 2 weeks. Today, we're just going to kind of go through the upper to middle crust. I'm going to talk lots about it, lots of different topics about it, and then introduce the lab assignment you're going to do this week, and then I have a rather aggressive schedule for next week. So let's just make sure. I know Yajing has already touched on point 3 pretty well, so I'll probably just go back and try to fill in some rock record details about what she's already discussed. And then because a lot of the profs that are lecturing this class work in continental environments and continental orogenies, I'm going to talk more in detail about the subduction environment, what the faults look like there, because they have the biggest earthquakes, and we're highly motivated by biggest earthquakes. And then at the end, kind of a little bit more theory, look at the stress in a little more detail, and maybe even bring in a little bit of hydrogeology in the way that the hydrogeologists think about faults and induced seismicity, which I'm going to have to borrow from Yajing anyway, but it'll be fun. Okay. So the first thing I want to do is just define what the seismogenic zone is. The seismogenic zone within the Earth is the part of the Earth where earthquakes nucleate, where they are most frequently detected. So it refers to a zone, like a volume of the Earth, where earthquake sources are common. And I went back to look for the original definition of this because it seems pretty straightforward, like it's the part of the Earth where the earthquakes come from, but in fact, it's a hard thing to define. And I think the first step toward defining it was actually the discovery of the Wadati-Benioff zone, where this was independently discovered by 2 seismologists basically working on the same thing at the same time. So this is a figure from a 1949 paper, and you might recognize the coast of South America here. And what they've done is locate the epicenters of all of these South American, what we know now to be the South American Trench there, earthquakes, and then to actually locate them well enough to start plotting them in 3D on these cross-sectional transects. So here's this bracket A. They've taken all of the earthquakes that fall in that bracket, projected them onto a single plane perpendicular to the coast, and they come up with a cross-section that looks like this. And they've drawn a line through it, and you can see that this is a very early take on what a subduction zone should look like, because their layers of the crust do not actually go along the line where what we now know to be the subduction plate boundary. Like they've drawn the layers right through, but they found that there is a big structure there that seems to be the earthquakes at the top are sort of around it, and then there's this second kind of patch of very deep earthquakes when you get down to about 660. So I don't know if this would hold up geometrically today, but all the way down South American margin, B, C, these 2 more brackets, they've got this same structure where they have a dipping plane of earthquakes that's going underneath the continent. Oh, is my mouse not moving on there? Dang it. How are we supposed to do this? No, it looks not moving. Oh, maybe this mouse will move on there. Sorry, hang on a sec. We don't have another mouse, do we? No. Okay, I'll just have to be like extremely verbal about where I'm pointing. I'll go to find a mouse. Okay, so this figure is also from Benioff's 1949 paper, and this is where he starts the interpretation. He's got a big thrust fault going underneath the Andes here. He's got it shallow under the Andes and then changing in dip to get steeper. And this is his explanation for the distribution of hypocenters of these earthquakes, which is starts to look a lot like a seismogenic zone, only the displacement on this thrust looks real small compared to what we know it to be today. Okay, so fast forward a couple of decades, and in 1964 we had the Good Friday earthquake in Alaska, 9.1, 9.1, yeah, right. We have consensus here, it's 9.1. And the amazing thing about this earthquake, one, luckily the population of the area was pretty low at this time. This was before oil was discovered in Alaska. Two, the population was heavily leaning towards scientists and geoscientists because there was so much exploration activity going on, and the survey was in a major mapping campaign up there. And one of the things that they were doing was coastline leveling. Hi.
Yeah. I don't think the mouse is.
Just wondering if there's any way to.
What you can do is you can annotate.
Oh.
Or wait, you control. I'm not sure if I can control, but you can annotate. You
Oh
can
my
always do like spotlight mouse.
Oh, superstar. Thank you. All right. All right. Okay. Let's see how this works. Okay. So what this map's showing, this is from George Placker in 1965. So imagine yourself, you're a young geologist, just finished your PhD, you just got your first job with the US Geological Survey. They send you to Alaska, and basically as soon as you get there, there's this giant earthquake. This is like the moment of your entire career. So George Placker went out and he did a couple of things, you know, with other people, it wasn't just him, but this paper is a single author paper. He went to all of these kind of areas of the coastline. Can you see that? Oh, it's working. Oh, this is fun. Okay. Oh, change color. All right. Okay, we're just going to go green for now. Went to all these areas of the coastline that had been recently surveyed and was able to resurvey them. And in doing so, came up with these contours that show the uplift. This is the zone of maximum uplift here. The zero contour line is here. Yeah. Zero contour. So out here, trenchward of most of the big cities in Alaska, we have an area of uplift. And basinward, or on the side of the continent, here's the Aleutian arc here. So this whole area.
Wave, please. Hey, Christy,
Yeah?
can you use a slightly brighter color?
Oh, okay, I gotta figure out how to change colors.
Red.
She's like red and blue.
Yeah, that'd be nice.
She's just outlining stuff.
Or maybe a thicker line.
Ooh, ooh. How about that?
Yeah.
It's better.
You see that?
So here's your area of uplift, and then back here, deeper in the fork, they have found an area of subsidence. And there's some interesting topography around the uplift. If you can see here, the contours are in meters. So 1, 2, 3, 4, 8, 4 meters. There's the 8-meter contour here. So there's a big discontinuity in the amount of uplift just here on this little island called Montague Island. So George Placker and his buddies were they basically hired a fisherman to drive them around, went island to island, and looked for places where the land that was previously underwater, that was populated by mussels and various things, was all of a sudden lifted way above sea level, and they mapped that. So out of this, Placker was able to draw, oops, uh-oh. Oh, yeah, oh, crap. Can you still see my scribbles? Clear? I'm a drum. Okay. Sorry guys, this new to this kit here. So Placker drew this awesome cross section across the whole earthquake rupture zone, basically. So here's the trench out here. Draw that. The Aleutian Trench. The volcanoes. We have this low-lying zone where Cook Inlet is in here. which corresponds roughly to the area where you had subsidence in the 1964 earthquake. And then somewhere around here is the zero line, and then everything between this area and the trench had uplift, and there was a spike of extreme uplift right around what's now called the Patton Bay Fault, which is there at Montague Island. And so these are some aftershock locations, not apparently falling on any particularly obvious structures here, but you got to keep in mind that there's no seismometers out here, so they're locating these based on seismometers that are tens or hundreds of kilometers away. They don't have any on the islands at that point. But what Plafker's drawn in here, which differs from the last model that we looked at, is this kind of thrust, subhorizontal thrust, that divides oceanic crust and mantle of the Pacific plate from continental crust of North America. So he's moved from like, oh, there's a thrust fault there, to being like, basically, this is the plate boundary thrust, which is a big development. Okay, clear. Uh-oh, clear. Okay. So fast forward another few decades. This is a paper from Roy Heinemann, who works at the Pacific Geoscience Center in Sydney. And by now, we have the concept of a seismogenic zone. So we understand that there's an area that doesn't quite extend to the seafloor most of the time, where earthquakes are abundant. And they've just colored this in with a big black line here, saying this is like the major earthquake source. And then it sort of trickles off with depth. Unclear exactly what ends it there. There's a second seismogenic zone that's imaged down here in the mantle. But what this paper is about is trying to establish exactly what the limits of the seismogenic zone are, what basically starts earthquakes happening up near the crust, and what finishes them down as you get deeper in the earth, and trying to attribute some kind of cause to this. So, yeah. So the argument put forward in Heinemann et al. Is that it's temperature controlled. So the temperature doesn't exert necessarily the direct primary control on the rock properties, although in some cases it is that. But there's a big control the temperature exerts in controlling what the mineralogy of the rocks are, and different minerals have different rock properties with respect to brittle behavior. So there's kind of a dual effect. One is the rock properties vary with temperature, and the other one is mineralogy varies with temperature, which causes variation in the rock properties. So this figure is also from Heinemann, and he shows how, let me get my green pen again. I really would like to change color a few times. I'll figure out how to do that. So obviously the scale of this one is quite a bit bigger than the other ones, but so the seismogenic zone is up here near the trench, and he's got the end of the seismogenic zone happening because this is where the plate boundary fault intersects the upper plate moho. So above the moho, you have continental rocks, presumably strong rocks. When they're in contact with the lower plate, you could have high stresses and strong friction. But when that subducting plate gets in contact with serpentinized mantle, or with mantle that it can then serpentinize, because remember, it's carrying a ton of water down with it. Serpentine is a slippery thing. It's a sheet silicate with some really weird properties, and it's very deformable, and it's, when we do laboratory tests on it, it has some of the lower friction of any minerals that we find in the upper parts of the earth. So the theory was basically that you should have earthquakes as long as your upper plate is strong rock, and then when you're below that and you're in contact with mantle, that you should stop having earthquakes. So that explains one end of the seismogenic zone. The other end of the seismogenic zone, in most cases, we don't have microseismicity going all the way out to the trench. And that is explained partially because these rocks that are coming in and subducting, and we'll talk more about this next week, but this is basically like ocean floor ooze. It's just goop. Like, it's not very strong. There's a lot of clay minerals in it, really high pore content of water, which translates into high pore pressures as it starts to subduct. So there's a little bit of this kind of up-dip area where the rocks are just too weak to ever build up elastic strains that would be released in an earthquake. So at some point with depth, those sediments start turning into a rock, and then you kind of acquire more seismically favorable properties as you go down. So this kind of defines an updip limit there. It's kind of annoying that I have to clear that drawing every time. Okay, so there's another line of thinking about it. So that was sort of compositional and thermal, but this is a figure from the same paper. And now we've moved across the Pacific. We're in Southwest Japan. So here's Shikoku Island, for those of you who are familiar with this area. And these two loops here represent the estimated rupture areas from two pretty large earthquakes. What are they, magnitude 7s? Magnitude 8s.
8.2, 8.4.
Ooh, 8.2, 8.4. Respectable, damn respectable earthquakes. 1944 and 1946 that happened here. And it's sort of a busy diagram, but here's the trench. So here's the Philippine sea plate coming in and subducting here. And these contours, 150, 350, 450C, represent the modeled temperature on the plate interface as it descends in the dip direction, which is northwest here under Shikoku Island. And these little contours here, 20, 30, 40, are showing the depth of that plate interface as it descends to the northwest. So based on these, I think are estimated from tsunami models. Oh, I should have checked. Anyway, I forget what they're estimated from, if it's actual seismic data or tsunami models. But the thing to notice is the correspondence between, say, about 150 degrees C. So that would be about the estimated temperature when the shales and the mudstones and stuff that make up the subducting sediments are actually undergoing diagenesis. They're starting to, the clays have destabilized. And so they're giving off a lot of silica into solution. A lot of the organic material that might be in those subducting sediments has started to produce oil and gas, which also leads to carbonate sedimentation. And those rocks are starting to compact. So all of these different things that contribute to the diagenesis of the sediments have started to take activity. And by 150 degrees C, you almost have something that resembles a rock. So this is going to be the thermal control on where the rocks get stiff enough to actually release energy in an earthquake rupture. And the updip limit of these kind of rupture patches corresponds somewhat, squint your eyes, to where the limit of the earthquake rupture was the kind of the limit of where we expect to have rock-like properties. Now at the same time, the sediments have a lot of quartz and feldspar in them. And quartz and feldspar will start to potentially behave ductily in the range of 350 to about 450 degrees C. So we clearly haven't reached the continental moho and the overriding plate yet. But if the sediments are the controlling lithology that's in the plate interface, then they are undergoing their brittle ductile transition by this time. And when they do that, we hit the limit of brittle behavior, which approximately corresponds to the down dip limit of these rupture patches. So this is without changing rocks to explain the down dip limit. We have a direct thermal control that changes the rock properties that limits the size of the earthquakes that happen there. Okay, so this was originally a figure from the Sam Heinemann paper of 1997, which I, as a young grad student, redrew at my advisor's request because he didn't understand Adobe Illustrator. And I added a few more margins on here. So this is published in a paper by my advisor in 2007, which was several years after I drew it for him. And by this time, he actually had got Illustrator himself. But the point of this figure, okay, so we have many different famous subduction zones on here: Alaska, Chile, Southwest Japan, which we just looked at, and then here's some Central American ones. These are all in Mexico, and Oregon, the southern end of Cascadia. And the plot is in the x-axis. It's the deformation distance from the deformation front, so that's just about out by the trench. It's right where you start seeing deformation, the accretionary wedge. So consider this kind of the trench out here. And on the y-axis, we have temperature. So the temperature increases with depth for every one of these subduction zones, but not at the same rate. Just because subduction zones, depending on the age of the plate, the dip of the plate, the speed of the plate, they'll warm up at different rates as they go down. So these are the estimated temperatures from thermal models on the plate interface for each of these subduction zones. So the curves, let's just look at Alaska. Why did I make a dashed line here? Oh, this is supposed to be the upper stable sliding zone where you have no earthquakes. And then right here we have the up dip limit of the earthquake source region. And this represents the distance on the plate boundary, which is in the seismogenic zone. So for Alaska, that's a really big plate interface. And that's because it's relatively cold. So that means that the shallower the dip and the colder it is, the longer the plate will be in that brittle zone. And effectively, that makes more fault area available for rupture. So your rupture magnitude, your potential magnitude can be greater. And then we've cut it off here where this is the depth where the plate interface intersects the moho of the overriding plate. So everything below here might see serpentine in the fault zone and be probably slippery. And so for Alaska, that happens before you would even hit that brittle ductile transition for the sedimentary rocks that are subducting there. So that is a big geometrically controlled seismogenic zone. Same thing for Chile. You hit the moho before the plate gets hot enough to actually undergo its own brittle ductile transition. But some of these Mexican ones, they get hotter a lot faster as they get away from the trench. And so these ones would actually undergo a transition to ductile behavior before they reach the upper plate moho, which is all the way down here. And then Cascadia is a funny one because there's so much sediment subducting there that the temperature at the trench is not the 4 degrees C that we call seawater. The plate interface is buried under kilometers of sediments. The plate interface is already hotter. So that's why it starts way down the axis here and not at the origin. So, yeah, so these roughly match, like the Nankai map we just looked at. There's a rough match between where we would predict to have the seismogenic zone and then where we actually map it in terms of looking at epicenters of earthquakes showing up. Okay, now Cascadia is a weird one because we don't have the two things we need to really objectively define the seismogenic zone. One is an observation of a great earthquake to see like where did the radiated energy actually come from in space? Can we draw a circle around it, like the Nankai example? We don't have that. The other thing we don't have at Cascadia is a lot of background microseismicity. So the best proxy for understanding what the seismogenic zone is in Cascadia is probably the geodetic observations, like modeling which part of the plate interface is locked and how that corresponds to the surface deformation in the forearc. So we can do thermal models of it, and this is basically the same format as the one we looked at for Nankai. So here's the trench. Yeah, the scale of this map is different than the one we looked at for Nankai, but here's the trench. Here's the model 350 degree contour. Here's the model 450 degree contour. So if you remember from Yajing's lecture, this area out here is, for the most part, locked. And this transition zone, which mapped to the transition zone here, just thermally defined, actually corresponds pretty well to some of the areas where we start to see ETS occur and tremor source, and that stuff extends even farther landward, so down dip into higher temperatures maybe than the 450 degree contour. I should have superimposed a real and modern map over this, but instead I'm scribbling on it so you can get what I mean by that. Okay, moving on to continental faults. This guy, if you don't know this guy already, Rick Simpson, he's going to pop up a lot in my lectures because unfortunately the guy had a lot of really good ideas and the rest of us are still running around proving them because he wrote a lot of really almost clairvoyant papers off almost no data. He's just a really smart guy. So you're going to see him from the 70s, 80s, 90s, 2000s. He's going to pop up a lot. Yeah, he's like a old person's radio station. So this figure is from a 1983 paper where he starts defining what the seismogenic zone looks like in the San Andreas Fault. So this is a plate boundary fault, but it is a continental transform, and it is subvertical, and it's several hundred kilometers long, and the thermal structure and the composition of the crust, it being a continent, varies on much shorter length scales than that. So if you go north to south, you go from the San Andreas down to Mexico to where it goes offshore in Northern California, which is, what, about a 12-hour drive. If you wanted to drive the whole San Andreas Fault, it'd be about 12 hours on the highway. Yeah. I've done parts of it. I've never done it in one go, but it's like bucket list. But so he's taken a bunch of transects in places where they had good density of seismometers. Oops. Let me just get my pencil back here. I don't know how to change color.
Are you using PDF viewer or?
No. This is the Zoom. Oh, wait. Okay. Sorry, there was a green box. I was drawing in green. Now I got a red box. I'm ready. Watch this, you guys. Oops. Here's red. Woo! Okay. So here's in Central California. This is all the earthquakes that happened in 1976. And so he's got a histogram with depth showing this is 0, 5, 10, 15, 20 kilometers. And this is just percentage of the earthquakes in this particular region during this particular time. So in Central California, he's got 754 earthquakes, and only a couple of % of them are in the top 3 kilometers, and then you start to see an increase, and by the time you're at 5 kilometers, like 20% of your earthquakes are in that 1 kilometer between 4 and 5. And then there's a slow decay, and then by the time you get down to 15 kilometers, no earthquakes left. So this is a really well-defined seismogenic zone, and it's basically telling you that your seismogenic zone goes from, say, 4 to 12 kilometers, and that is the brittle zone in the North American crust at that point in the San Andreas Fault. This one's a little bit scary because there's a big reverse component. This is at the Big Bend in the San Andreas Fault. Imperial Valley, as we're getting down toward the south, we actually see a deepening of the San Andreas seismogenic zone a little bit there. And then this is a kind of a fun anomaly. This is in the northern part of the San Andreas Fault where there's an active hydrothermal system. There was actually some slab window volcanism here only about 4 to 6 million years ago. And so there's like really young rhyolites and like cones and petrified wood lying around everywhere. But it's an active hydrothermal system, and the geysers is actually a hydrothermal energy plant there, so it's being exploited. You can see that where you have a high heat flow, your seismogenic zone moves up. Oops, dang it, moves up in the crust. So we end up with a very shallow seismogenic zone, a lot of earthquakes here that are probably associated a lot with fluid flow. And below about 5 kilometers, the crust is hot and we have no earthquakes. All right. So here's a leap we can make. Since we have defined a seismogenic zone in terms of the thermal structure of the Earth, the other thing that's well defined in terms of thermal structure of the Earth is metamorphic phases, metamorphic phase diagram. So this is a metamorphic phase diagram. Oops. Yeah. Okay, I'm just going to blame autocorrect on this one. Obviously, I don't mean metabolites. I mean, this should say metabasites. Ooh, can I? Yeah, okay. Yeah? All right. Sorry. Okay, that should be metabasites. So here's your phases in a metabasite. And what we did, this is again my advisor's paper in 2007, Casey Moore, we took the temperature limits and we estimated the depth of those temperatures for a range of subduction zones, calculated the pressure in MPa just using an assumption about crustal density, probably 3,000 kilograms per cubic meter, and drew a blob over the metamorphic phase diagram that includes all the rocks that should be metamorphically stable in the zone where the earthquakes are coming from. So this includes all of those different subduction thrusts at different depths and thermal structures. So any one subduction thrust might, only be here or only be here. But if we encompassed all of the world's subduction thrusts where brittle behavior is promoted, it would include blue schists. These are kind of sub-green schist grades that we love to look at. So these are the rocks we're looking for if we actually want to look for the rock record of seismogenesis in a subduction zone. If we're in the continents, a lot of the rocks are granitic, which are metamorphically pretty boring. But so I just added this kind of blue lines to show if we had politic rocks, which are metamorphically a little more exciting. I put the aluminosilicate triple junction on here. And this blue box here represents the seismogenic zone as defined for the San Andreas fault. So kind of anywhere in the 5 to 15 kilometer range. And the temperature limits, again, from about 100 to maybe 350 degrees C. So in that case, it's probably a smaller region just because I used one fault instead of a spread of faults to fill in the region. But yeah, I mean, the take home from that is if you see sillimanite, it's not an earthquake. Okay, that was kind of a joke. No one's laughing. All right. Okay. So now that we know which rocks we're looking for to understand the rock record of the earthquake cycle, let's look at what deformation mechanisms are active in those rocks at the conditions we're interested in. So pretty much everything that Laurent talked about was crystallplastic deformation. And once you get into the seismogenic zone, it's basically defined by a place where crystallplastic deformation cannot keep up with the imposed deformation rates. So we're going to be dominated by frictional sliding, particulate flow, cataplastic flow, solution creep. Maybe we have dislocation creep in some of the weaker minerals, as long as they don't dominate the rock properties. So for example, if we have calcite cement in a sandstone and it's deforming at 200 degrees, you may see plastic microstructures show up in the calcite. That's not enough to make the rock macroscopically plastic. So it'll still be dominated by the framework grains of quartz and feldspar that are not ductile at those conditions. And then there's some weird stuff that happens at very high slip rates. So I kind of broke this down by looking at the slip rate that each one would be active at. Ductile deformation, as we reviewed, has specific relationships that govern it, that we understand, that are experimentally demonstrated and calibrated, that relate the deformation rate to the strength, those rheological laws. And so we know that these creep mechanisms have to operate slowly. They're rate limited. Frictional sliding is not rate limited. And I'll talk about that a little bit more. And I know Yajing talked about that a bit too. But frictional sliding and then particulate flow or cataclastic flow can happen slow or fast. And one of the big challenges, I think, in earthquake geology generally right now is to learn more about how those processes act at different velocities, how they're restricted, and then how they record in the rock record what kind of slip velocities actually took place. And then we have this sort of freaky and essentially brand new field of looking at dynamic weakening mechanisms. So these are weakening mechanisms or reactions that occur in the rock only at very high slip velocities. Most of these are activated when slip velocities exceed something like a centimeter per second. And since earthquake slip can go from a centimeter per second up to a meter per second, even 10 meters per second in some cases, these are the deformation mechanisms that dominate during the seconds or minutes of an earthquake. Okay, so this might get a little esoteric for a second, but I put this slide in to convince you that studying earthquakes, you're really studying a frictional process. So this is brought from Brace and Byerly in 1966, and these are rock deforming people, so they do these lab experiments, which I think Yojing talked about, where you basically take a cylinder of rock, and you can either put it intact and put some load on it with some normal stress, and deform, increase this load until the rock breaks, or you can cut it with a saw and put a pre-existing fault in there. And then when you load it until it breaks, what you're breaking or what you're starting to slide on is this fault, which has some roughness to it that's determined by your saw cut. So if you do the first thing, you're actually going to, the properties of this fracture when it forms will depend on the spontaneous and original properties of the fracture that the rock makes when it breaks. So this is more like a real fault. So there's these, in this set of experiments, they did both. And what they see here is, okay, so this is the force, this is the load that they're putting, the vertical force. And this is the displacement. So this is how much basically this arrow and this arrow have advanced toward each other during the experiment. And in the originally intact experiment, they start out with 0 displacement and 0 force, increase the force, the rock starts to squish, and initially it squishes elastically. It's just shortening, but if you let go at this point, it would probably go back. It would probably rebound. But they get up to some point, which is basically the strength of the rock, and the rock fractures. And so here at FR, the fracture takes place and this little fault forms at some spontaneous angle. Then they continue to force the machine, so they're forcing the rock, and it starts to slide on this new fault. And as it does, this funny sawtooth pattern emerges. These are stick slips. So they've got a high force. All of a sudden, it drops down. The rock is still shortening. So this drop in force and a sudden shortening represents a little slip event on that new fault. Then they slowly load it, and it follows the same slope as the original loading. And then a second stick slip event occurs. So as long as they're externally loading this, they get these pause, slip behavior. And in fact, in the experiments where they put a saw cut in it, they basically see the same thing. Except it's stick slip all the way. It's stick slip. They don't have to get to the point where they would break the rock, because they immediately, as soon as they start loading, they start getting these stick slips. It's worth noting here that the axes are not the same. So the force of 2 kilograms, and the 4th kilograms, the 2 is up here. So this rock was a lot stronger. It took almost 4 before it fractured. This one starts sliding down here at less than 2. So these peaks are about equivalent to these lows down here. But again, we get the stick slip behavior. And the funny thing is that not all of these sticks and slips are the same, right? Some of them you have a really big slip where you do a lot of axial displacement and a lot of drop in force. And some of them are quite small. And the big ones are farther apart and the small ones are closer together. So this kind of stick slip pattern is actually a pretty good analogy for earthquakes. And the great thing about the Brace and Byerly experiments is it kind of puts a mechanism we knew since the 1906 earthquake, and since a publication by Reed in 1910, that the forcing, the external forcing to drive the earthquake cycle was coming from elastic energy released from the plates. But there's nothing about that inherently says you're going to have a repeating cycle of stress drop events. I mean, you could elastically load things forever and just load more and more plate and eventually have one giant earthquake that rips apart the globe. Like, there's nothing intrinsically quasi-periodic about the elastic rebound theory. So here's the way we think about these frictional systems. Did you go over this already? Did you block slide?
A little bit in the column stress
Okay.
idea of the.
Okay, I'll just do it again. Okay. So we'll take this super simplified world here, which, by the way, is how we do it with math. No complications. Sky blue.
Actually, Christie, I have a question regarding the previous slide.
Oh, yeah.
How big is the sample? Because
How big is the sample?
the actual displacement is like 2 millimeters maximum, and then since that each of the stick event was only sliding very tiny along the cut or the fracture.
I don't actually remember from this paper, but usually with this type of apparatus, it's like a 1-inch core or a 3-inch core in diameter. So pretty small.
Not entirely offset.
Yeah, because they're looking at force instead of stress.
Yeah.
Yeah, that's an important consideration. Okay, so here's a super simple example. And actually, if you go to the USGS website, they have directions on how to build one of these to demonstrate this to students, which is kind of fun. What you need is a brick. Oops. A brick. Draw. There it is. It has some mass. So that mass times the area of the contact of the brick and some surface, and it could be a tabletop, it could be a piece of sandpaper, it could be whatever you want, gives you the normal stress that is acting on the surface. Okay, let's say you're going to pull the brick along, and you're pulling from here with some force, which you can increase arbitrarily as you want to. But there's a spring in line with your handle, and the spring has some stiffness, K. So as you pull, the force is applied to the sliding surface of the brick, but it is moderated by whatever's happening in the spring here. So, all right, so let's consider a couple of end-member cases here. If the spring is super stiff, so it's effectively not a spring because it's so strong that you can't stretch it, then when you pull with some force here, when you pull with some force here, the spring doesn't stretch, so the pull gets translated directly to the brick, and you just pull the brick along. So in this case, if you look at my little plot here, with time, when you pull that brick along at some constant force, you'll get a constant velocity, so the brick just moves linearly with time. And that also means that the stress here is going to be constant, so the shear stress stays flat here. And the value of that shear stress will be whatever shear stress is exactly required to move the brick. Okay. So that's our one end member. All right. Ooh. Okay. All right. What if the spring is a real spring and it's stretchy? Then we can have kind of two end member behaviors for this interface here. Sorry. For this interface here. One is that when you start pulling it, it gets stronger with increasing speed. And the other one is when you start pulling it, it could get weaker with increasing speed. So if it gets stronger with increasing speed, we call that velocity strengthening. So let's take this example where we have a stretchy spring and we have a velocity strengthening fault interface here. So we have a stretchy spring. So as you start to apply force, the first thing that will happen is that the spring stretches out, and so the brick won't actually start to move until you've stretched out the spring a good deal, and you've loaded that spring, you've given that spring some stored elastic energy. So in our little plot here, we have this no increase in distance, but some increase in time, during which time we're loading the system. Shear stress plot's not right. I'll fix it. And then once the spring gets stretched out so that its resistance is equaling the force you're putting into it, that is actually going to approach a stiff condition for the spring, and it will start translating that motion back to the brick. So the brick is going to start accelerating and go up here. And the shear stress on the system then is actually not correct on my plot. The shear stress on the brick interface is going to jump up. And then once you reach like a forcing rate that will allow this to slide at a constant rate, then your shear stress is going to reach a constant value that corresponds to that constant rate. I'm sorry about that. I did make a new plot. I just forgot to put it in my slides. Ultimately, this is going to look kind of similar to the other system. And that's because if you accelerated this any more, the brick would actually, the friction on this surface would actually increase because its velocity is strengthening. So you reach this equilibrium point where the brick is in a steady state creep and it's going at a constant velocity. Okay, this is the more fun example, and then we'll take a break. Let's imagine that you have, I'm going to clear this. Okay, let's imagine you have the same case, you have the stretchy spring, but this time the interface between the block and the table is velocity weakening. That means as you accelerate, the block, the frictional force resisting sliding will actually decrease. So same thing happens off the bat. We pull the slider. We pull the slider, and the first thing that happens is that the spring stretches out. So we have the same thing where we have a time with no displacement at the beginning while we load the system. Then, when we reach the stiffness of the spring, this is where the system is different. Because when you reach that critical stiffness and you translate some of that motion back to the block, instead of just pulling along at a constant rate, once you accelerate the block, the frictional resistance decreases. So the block can actually accelerate and bunch up the spring again. So here he is jumping forward, shortening the spring. So it's mining the energy that you put into the system from your constant pulling as well as what you stored in the spring. It's accelerating and it's overreaching. So the spring actually gets unloaded, the shear stress in the system drops. Now you don't have any force on the block again because it's stopped. So there's a period of time again where the block can be stationary. And when the spring reaches that threshold again, then all of that spring energy and your constant pull is exerted on the block gets weaker and slipperier as it goes, and you have another stick slip event. So this is like a good model for the earthquake cycle, and this is why we know two things about earthquakes. One is that stress drop that we see in an earthquake system is the stress that at peak loading, we had a bunch of stress stored in our elastic component, which could be our crust, or in this case, our spring. And the stress drop in the system is associated with the sliding event, and that returns to a low stress system in the spring, in the elastic component. The other thing that we know is for this behavior to happen, that interface has to have this property of being velocity weakening. It has to have the behavior that when it accelerates, the shear stress goes down. And the shear stress is, of course, a function of the friction coefficient. So those two attributes basically describe all the stick slip behavior in this system. And we go forward with the assumption that some part of the Earth has properties that are analogous to this, so that this model can describe the earthquake cycle. So I think that's a good place to take a break. Everyone ready for a break? Oh yeah, McGill looks ready for a break. Okay, so why don't we take 10 minutes? I have 2:32. Why don't we come back at 2:45? 13-minute break. We'll start again at 2:45.
Sounds good.
Look at everybody again. It's kind of good. I can't see anyone when I'm watching.
It was the earthquake physics. It was an earthquake physics last week.
Yeah. Good. So I didn't talk about this in this class, but I talked about that for the earthquake physics class, which is identical. This population.
It's okay, it's a good refresher. Christie, where can we get the thin sections?
Oh, they're sitting on my desk. Yeah. All the other schools got some of Catherine's rocks, but sent all those out. You guys are only getting other rocks you haven't seen before. And Catherine hasn't seen before.
So funny, we were just talking to Eric about how none of us have seen Cat's Rocks and seen people look at the phosphorus.
I actually don't have her with phosphorus in section, so let me do the ones from the other outcrop.
Oh, yeah, well, the gravel pit.
Gravel pit.
Where are the ones that we're looking at from?
Some I borrowed from Jamie, from Sierra. I think there's one from Japan, from Moody.
Oh, cool. Like one of those sample?
No,
That was nice.
one that I acquired by stealing it from an advisor. It was a gift to him when the first subduction zone pseudotachylytes were discovered. He made a visit to Japan to see them, and they made a gift of a couple of thin sections to him. And then when we found pseudotachylytes, he gave me his honorary thin sections so that I could learn more about what they should look like. And I never returned them.
Solid.
Solid. Yeah, that was in 2004. Never mind now. He's forgotten.
Nice.
Have you heard anything from Kat?
We turned in our assignment this morning. But, yeah, I know.
Anything else from her last night? Did not contain any information about whether she's decided to go for a PhD program, one or the other. I don't want to nag her because she's on vacation. Just, I don't know.
There was something weird about one of our offers. I forget which school, but like they would not formally accept her until she formally told them that she would go there.
Yeah,
That's just weird. I forget which one it was.
it was Pika cells.
I wouldn't
Was on
get here.
Okay. Everyone ready to go? Should we start again? Yeah?
Oh, is everybody back?
Alright.
Everybody back? Okay.
Yeah, I think we're good at Queens.
That's your ears.
Alright. Let me just share the screen. Yeah. Okay. Everybody got slides? All right, I'm not on mute. Everything's good. Okay. Okay, so obviously, in order to tackle these problems, we need to know what the frictional properties of rocks are. So Byerly, 1978, did this massive compilation where they basically took all the rocks. So if you look at this, ooh, where did I get that panel before? Oh no, where's my annotate? Oh, there it is. Okay. Basically took all the rocks and plotted their frictional properties. Sorry. Okay, so we have granite, fractured, ground surface, limestone, gabbro, dunite, sandstone, faulted, saw cut, granodiorite, gneiss, myelinite, plaster in a joint in quartz monzonite, quartz monzonite with joints, westerly granite, chlorite, serpentinite, illite, kaolinite. Okay, whatever, you can read it. These laboratory tests they were doing in the 60s and 70s were at low speeds, 10 microns per second, 100 microns per second. So what we get from these tests is a shear stress to normal stress ratio, or a friction coefficient at low speeds. And that's what you see here. If you take all of these rocks that he's plotted here, you get this equation where shear stress is some constant, which represents the y-intercept on the graph, which would be the cohesion, plus some factor times the normal stress. And this factor right here is defined as mu, the coefficient of friction. This hopefully is familiar to everybody. The big surprise and interesting insight out of this is that all of these rocks, doesn't matter what they are, they fall on the same line. That line has a slope of something like 0.6 or 0.7. You see both of them bandied around, and that value is called the Byerly friction. Like any normal rock, slow slip speed, 0.6, 0.7, that's Byerly's law of friction. A couple of things, like the details of this plot. One is where stresses are very low, the friction coefficient appears to be higher. And then the other one is that these are, yeah, okay, so the little tiny X symbol here is for these experiments where there's a bunch of these sheet silicate minerals, chlorite, serpentine, illite, kaolinite, montmorillonite, vermiculite, and those are labeled with letters in here because they fall below the line. So their shear stress, their ability to resist shearing for the same amount of normal stress is much lower than your average rock. So basically, we can divide the world into rock and then clay. Rocks have Byerly friction at low speeds. Clays have lower frictional values, and they vary. So if you're going to do a set of experiments, there's M line. These would all have different slopes, but they're all lower than the 0.6. And some of them are quite low. Vermiculite, montmorillonite, these are the really expansive clays. So their slopes are like even half, 0.3, getting down to 0.2. This is very low friction materials. These are the lowest frictional materials that we find at the surface of the Earth. And now we're drawing. Okay. So that establishes kind of what our baseline friction coefficient value is. Now we've shown in the previous set of slides that it's the variation of that frictional value with slip velocity is really important. So this plot is from Chris Morone did this massive summary paper in 1998. It's basically a textbook. He actually teaches a class that uses this one journal article as the textbook. No screwing around. I'm just going to give you this one figure from it. This is the basis for what we call rate and state friction. So you start with your Byerly friction, and you say, okay, let's vary different things about this system. Let's vary the rate at which we're pulling that brick. Let's vary the time in which the brick sits stationary before we pull it. Those type of things. it turns out that each one of those variables actually does affect the mu that you observe. So this is, let's see, if we look in the upper right corner here. Should I get a different? Yeah, okay. Here's a friction coefficient, which is nearbyerly, so we're 0.62 to 0.66. This is quartz gouge, and I'm going to say something kind of snarky here, but this will not be a gouge where somebody went to a fault in quartzite and collected the fault gouge. This will be somebody bought a quartzite from a laboratory or a quarry, ground it up, sieved it, made sure they had a constant particle size, and all the particles are going to be super angular because they just like probably smashed it with a hammer, and then they put that in their instrument. Obviously, I don't have to tell you how I feel about that. Okay, so it's a quartz gouge, but it's a fake rock. It's not like something you would find in nature. And so what they've done is they're sliding that rock in a shearing instrument, and then they're going to hold it for different periods of time. 100 seconds, 100 seconds, 10 seconds, 10 seconds, and they're going to look at how the friction changes between holes. So if they slide it and they're getting this constant value of 0.64, and then they hold it for 100 seconds, the strength spikes way up during that time. The longer you leave that thing stationary and intact, the higher the spike goes. Then they start sliding it again, it goes back to 0.64. But if they've only held it for, say, 10 seconds, the strength spike is not so much. And if you think what the importance of the strength spike is, that represents how much pull you have to have coming through the spring to get the thing started. There's resistance to starting sliding again. So obviously, there's something about how long surfaces are in contact that affects their cohesion or their friction coefficient that's going to change that relationship. Okay, the plot below that is for the velocity dependence. So here's another, must be a different quartz gouge because it has quite different properties. But it starts out at 0.545 for a value of mu, so still kind of just below the typical Byerly range. And that's the mu that you measure when your velocity of your experiment is at 0.5 millimeter per second, 0.4 millimeters per second. Then they do a step change in the velocity. They just accelerate the machine by a factor of 10 quickly. So then they're going at 4 millimeters per second. So again, you had a spike in the strength. And then when it stabilizes down to this constant velocity of 4 millimeters per second, the mu that they're measuring there is actually lower. The mu is decreased by 0.05 unitless numbers of friction when you accelerate to a higher slip velocity. So is this a velocity strengthening or a velocity weakening quartz gouge? Anyone? Literally anybody.
Weakening.
All right, we got an answer from McGill. Can you guys hear me?
Yes, we hear you.
All right.
Yes, yes.
Is it velocity strengthening or velocity weakening?
Quartz.
Somebody said weakening at Queens.
Sorry? Anyone have an answer?
We said weakening here.
Weakening? Okay.
Yeah.
I think you said weakening, which is correct. Excellent. Good job, team. That was a good use of 90 seconds. Okay, so this is the velocity weakening quartz gouge. So this talking about friction in this way gives us this kind of empirical, totally empirical relation we call rate and state friction, where you measure kind of a basic background friction, maybe a Byerly value, and then the friction is modified by some equation that involves the velocity and something called the state variable, and the state variable includes things like hold time and some other stuff. And what that other stuff is varies depending on your material and your application. So It's not a fantastically predictive law, but if you, through experiment, can establish something like looking at how this material changes at different velocities, like here's your friction coefficient and here's your sliding velocity in microns per second, like there's a strong relationship here that you can use to predict what would happen to this material during an earthquake. It would continue to run away when you got to those higher slip velocities. So every material behaves a little bit differently in this sense, and a lot of laboratory time is dedicated toward trying to refine and define the appropriate constants to use for different materials for these plots. The catch, the sticking point, is that because there's no direct mechanism behind this law, doesn't really describe why friction behaves in this way for one material versus another. We can't be confident that when we're extrapolating the laboratory results to a natural system, that we haven't just missed some really important controlling factor, or that we can actually extrapolate across the orders of magnitude of size or time or rate or whatever that we need to in order to use this to talk about a real earthquake. So it's quite a powerful formulation in terms of what you can use it for, but it is weak in terms of how well do we test how well it's doing to describe the natural system. And that's all I'm going to say about friction. Sorry, Ajay. We could talk more about it, but okay. So frictional sliding. The next mechanism that's really important in the seismogenic zone is particulate flow or cataclastic flow, and I want to make a small distinction between those two. So particulate flow is something that's common to soft sediments, snow avalanches, earthquakes, fault gouge, whatever you might find that's made of particles. And it involves a change in shape that's actuated. On a large scale, it's cohesive. On a small scale, it's incohesive because it's actuated by small displacements between grains. Here's a couple of grains. Here they are in the next plot, the same couple of grains. Ooh, is this the same grain? So the motion between these grains from one picture to another might be different for any pair of grains that you look at. But overall in the system, we can see a well-ordered transition. You know, this looks like a strain ellipse changing from a sphere to a more elliptical shape with a different orientation. So we could say it's undergone some shear strain or some rotational strain. So in detail, it's quite complicated, and it would be difficult to predict the motion of any one particle. But in the broadest sense, we can look at this as a continuum ductile deformation of the overall system. So this kind of deformation is favored when you have the particles are strong relative to the interfaces between particles. So these particles are not deforming internally. You're only seeing interparticle flow instead of any intraparticle flow. Okay, this is related to and often happens along with what we call cataclastic flow. Cataclastic flow involves particulate flow, but also you have deformation of the individual particles. They may actually start from an intact rock. So here's some experiments by Hadizadeh and Rudder, published in 1982, where they basically took some big porous sandstones, and they did deformation at different conditions. This one we've seen before. This is the development of a single through-going fracture. But depending on how you load this and how much pore pressure you put into it, the same porous sandstone will actually deform in a lot of different ways. And you can make it deform in a more distributed fashion. So we could start with one fault as the least distributed deformation. Then you might have the development of multiple faults. And then you might have a case where you have a lot of shape change here that can't be attributed to any one discrete structure. That means that there's lots of microfaults forming all through the sandstone and starting to break it up. And in fact, you can extend that all the way into the development of basically gouge layer, where your nice sand grains here that were intact, they can get broken up into like many small microfaults during deformation. So this one actually has maybe a through-going fault. We'll call him the winner. And then, but it also has a lot of smaller faults that developed in here trying to deform this rock. We call them the losers because they didn't actually manage to link up and form a through-going fault zone. But the bulk of this rock is still deformed. There's probably no part of this rock which you can look at it, you know, take a little piece here and find that it was completely undeformed and looked like your original rock. And then B is a really nice example of a completely distributed deformation. You can still see the original kind of, there's some sand grains in here, but they don't have their original kind of cemented sand grain boundaries like the original rock. They're completely bounded by little shear surfaces that are almost as frequent as grain boundaries, right? The spacing between these little microfaults is on the same order as the size of the sand grains. So this is almost completely distributed deformation. And because they're breaking through and cutting sharply across the edge of the sand grains and they extend along the margins of several grains, that's a cataclastic flow. That's a completely distributed cataclastic flow. So both particulate flow and cataclastic flow are really important in the seismogenic zone, depending on how hard the rocks are, how well cemented the gouge is, whatever. And the annoying part about both of these mechanisms is while they're super abundant, we know almost nothing about how they work. So we don't know, we know that both can happen very quickly or very slowly. And there's no fundamental structural difference between a rock that was formed fast or slow by one of these mechanisms. So trying to make sense of rocks in the rock record who have deformed this way is can be frustrating. So there's a whole class of deformation features that occur in the brittle realm that rely on particulate flow and cataclastic flow for formation. These are called deformation bands. I probably should have titled this slide Deformation Band. I'll just cross that out. I love this drawing pencil. So, all caps this. All right. Deformation bands. Oh, this is great. Okay, so deformation bands form predominantly in porous rock. They involve the rearrangement of grains, and here they are in like an outcrop scale view almost. This is 20 millimeters. They make these little tiny, you can see that there's displacement along them because they're offsetting the sedimentary layers in the sandstone. They're best known from sandstones. They basically form in porous rock. The oilies love them because they, or love them or hate them, I guess, because if you have this little band of super low porosity rock cutting through what would otherwise be a really nice reservoir unit, you have created an impermeable barrier for fluids moving through that rock. And so some of these actually dilate and some of them compact. Here's what they look like in thin section. Here's your deformation band. You can see that the grain size in here is smaller. Some of the sand grains were actually broken up in order to form this deformation band. And your pore space is much smaller too. So this thin section, it's a black and white photograph, but it was almost certainly a blue dyed epoxy that we put in here to make this pore space look dark gray. So here's a big pore in the regular sandstone, and then your biggest pores in the deformation band are like that big. So of course your oil doesn't want to go through there. So deformation bands, which are, obviously you can't image these seismically. You might get lucky and find them if you have some core samples, but they're going to completely change the properties of your rock. So pretty important for people interested in fluid flow in the crust. But if you're not interested in oil fields or fluid flow in the crust, you might still be interested in these because they are, by definition, they are itty-bitty structures. They're little, small, they don't get more than about 1 centimeter wide. They can get very long, hundreds of meters long, and only have 1 centimeter or 10 centimeters of displacement on them. And so we kind of have come to thinking of them as proto-faults. They're like the little larvae of fractures that are trying to link up and grow to become like a respectable adult fault. So we look at these to look at things like how do fault systems evolve over time. If you have an outcrop that has this set, you say, okay, here's a bunch of them that have linked up and they're making a bigger fault. Why does this even activate when you have a big fault over here? Now we have something like the development of a damage zone where you've got a lot of fractures. As you go away from the fault, they disappear. But how do these link up and connect to develop a bigger fault over the long term? These are a great way to look at the kind of fundamentals of the birth of fault systems. So this is also from the same Fossen paper. You might know Fossen because he wrote this structural geology textbook, which a lot of us have adopted because he has the best pictures. And it seems like students respond to that in a good way, best graphics. But he's a deformation band geek. He goes to Utah every year and just like pokes around the sandstones. And so he's classified the different types of deformation bands that you get out here. And so that can range from the compaction bands. Compaction bands here, like the one we just saw, where you have an increase in grain density and a decrease in porosity. Compactional shear bands. Oh yeah, some of these are just flattening features. Some of them are shear. You can have just a shear band that doesn't involve any grain size change, but does involve a rearrangement of grains. And then some of these are actually dilational, which is kind of crazy to think about. I've actually seen slides that look like this. It looks like the grains aren't touching each other, but in 3 dimensions, they really are. But you actually have a volume increase there, which is an interesting kind of feature. So any one of these might weaken or strengthen the rock and change your fault properties along the way. Okay, but I had to put in this picture of the Punch Bowl Fault in Southern California because most faults aren't in beautiful, pure, matrix-free, coarse grained sandstones. Most faults we see in the upper crust are in a mixture of sediment, maybe uplifted metamorphic and igneous rock, and they contain these phyllosilicates, which are, as we've seen from the Byerly plot, totally different. They're game changers. They're different than everything else. And we want to understand the fault. We need to understand what the role of the phyllosilicates is. So this Punch Bowl fault is a really famous fault because it's a little branch of what we think was active as part of the San Andreas system, but as the San Andreas fault has sort of moved around through time and abandoned the Punch Bowl strand. But it's a pretty big strand of a fault. It has about 40 kilometers of cumulative displacement on it, so like medium big. And the great thing about it is that it's exposed in like a regional park near Los Angeles. And Fred Chester, the geologist, his mom lives, so her backyard faces over this park. So Fred and his wife, Judy Chester, and his advisor, John Logan, who are all kind of famous fault rock people, spent a lot of time looking at this fault in detail as an analog for thinking about the modern San Andreas fault and how it works. And so Fred made a lot of contributions through this, mostly Fred and also Judy. But the interesting thing about this fault is that it's basically a sandwich of lots of different kinds of faults. So on one side of the fault, you have low-grade sedimentary rocks that were never buried more than a few kilometers. On the other side of the fault, you have granites and some high-grade metasediments that were the country rock to those granites. So the fault gouge that developed in there is a combination of materials from the sediments, materials from the granites, and the weathering products of all those materials. And that's a really important thing because in the shallow, we're still talking about this range of 100 to 350 degrees, where if you have hydrothermal fluids active in the fault, things like feldspars are going to be weathered to clays. And so that's why the only thing that really survives all that weathering process is quartz. So a fault gouge will typically have some quartz in it, and then clays replacing feldspars, clays replacing micas, and all kinds of oxides and funny things that grow by fluid rock interaction as you're moving stuff around in there. So in the Punch Bowl fault, we have, just on this one photo, you can see a couple of different layers. And I actually don't know which side was the sediment side and which one is the granite side here. I suspect this is the granite side down here. So we've got this layer of really broken rock, like badly broken rock. We might call this a breccia even, which has been altered and weathered. And in fact, in and around faults, oftentimes you see that all the feldspars turn a chalky white color because there's so much, say, kaolinite growing in the K-spar. They lose their translucency. Then we have this layer of pretty dark gouge, which has a strong fabric to it, a strong foliation. It's pretty fine grained. And it's also quite cohesive and hard. And I'm saying that because I can see hammer marks on the fault gouge where people have been trying to sample it. And this fabric, this inclined fabric to the fault zone, is cut off by this super sharp interface here, which we define as the principal slip surface. Oh, he's got a little arrow for it already. That's the principal slip surface of the punchbowl fault. And one of the big revelations from the Chester's work out here is that on one side of the principal slip surface, all of this gouge is made from granite or altered granite. And on the other side of the principal slip surface, all of this material is derived from sediments or altered sediments. So the conclusion that the Chesters made from that observation is that this eensy-weensy sharp surface here is the fault. Like, that's it. There hasn't been material mixing across this thing, even though there's been 40 kilometers of slip through it. So you might have like a shear profile through here that increases here, but the amount of strain in that little tiny slip surface is probably really, really high to have 40 kilometers of displacement and not be mixing any material along here. So then on the sedimentary side of the fault, we have a bunch more layers of different gouges that you could kind of draw out and define. And wouldn't it be nice if this was a color photo? But they put, 1985. They didn't put them in the papers back then. But then you get to this very chaotic gouge layer. And you can see that there's big folds, that you have an aligned phyllosilicate fabric, which might be kind of similar to what's happening down here, but it's been deformed. So it's not always parallel to itself. Then you go into this transitional zone where there's chunks of rock. Maybe some of it has some cements or some veins in it. Give it this light color. Broken, but you obviously have flow of the gougey phyllosilicate-rich gouge around these chunks of rock. So this is sort of a gouge and breccia. And then you transition into what looks like fractured wall rock, the high fracture density. And the punch bowl is not the only fault like this. There are tons of faults that basically have a similar structure that give us our kind of fault architecture nomenclature. So we often think of a fault of having a fault core. And I'm just going to switch colors here. The fault core would basically be everything from fractured intact wall rock on one side to fractured intact wall rock on the other side. We call that the fault core. Fault core. Is that at all legible? Better do something about that L. Fault core. Okay. And most of the time, but not always, you find the principal slip surface that's known in America as a PSZ. For y'all, I'm going to just describe it as a PSZ, principal slip surface. And faults can have many principal slip zones associated with them, one or more. In this case, there's really just this one that's identified in this particular part of the punch bowl fault. So the fault core is occupied by a wide variety of different fault rocks, gouges, breccias, foliated things, non-foliated things. Principal slip surface is a very sharp, discrete zone, and if you had a little thin section of the principal slip surface, you could probably go and find individual tiny grains of quartz and feldspar that are cut by these things. Like, these are sharp, they're like a knife. And then outside of the fault core, we have what's only represented by this upper corner of the photo here, or maybe down here. We have what we call the damage zone, which is really fractured wall rock. Should have, in general, the same composition of the wall rock. Maybe there's a little bit more advanced alteration there than you would find in the background wall rock. But the principal attribute of that is the high fracture density, and it decays with distance away from the fault core. Ooh. Okay. So the other elephant in the room here, or not in the room, but in the seismogenic zone, is solution creep. Solution creep is a deformation mechanism that operates by when you must have water in the pores of the rock, the solubility of any given mineral that increases with temperature, with pressure, is going to result in mineral getting dissolved into the pore water. Because the rock is strong and is supporting some kind of differential stress, the stress on the rock is different in different directions. There's a maximum principal stress direction and minimum principal stress direction. At the maximum, the minerals are more soluble in the pore water than they are in the minimum principal stress, which means that the points of very high stress on the mineral pore interface, you will have accelerated dissolution of the minerals. At the points of very low, if that same water that picked up a bunch of quartz from the high stress point flows to a low stress area, the solubility of the quartz is reduced in that water, and the quartz will come out of solution and be deposited. So this should be affecting every single rock at any depth in the earth. If there is water that is a thick enough film or abundant enough in the pore space that it bridges between areas that have different stress. So in a sandstone, that's just as simple as if you apply a vertical load just by burying that sandstone, then the interface on any spherical grain will have like high solubility and low solubility areas. So we know in the shallow crust this is a massively important mechanism, and the picture I'm showing here from Cox and Patterson is from experiments. But if you look at C, get my little pencil. Look at C. These are sand grains, and I'm sorry I didn't copy over what the value of the scale is here, but if these are normal sand grains, they're maybe 100 microns, 200 microns. And they probably started out as spherical sand grains that had contacts at points, like a box of tennis balls. And after this experiment where they've been in warm water for long enough with a differential load on them, those points where the tennis balls would have been sitting on one another are the high stress points. Those dissolve, they flatten out, and those contacts become kind of nestled like little pillows together because they spread out with the dissolution reprecipitation. So when you pull those apart, you can see these kind of form like you see in A, where there's this elliptical depression in the side of a sand grain. That's where another one was sitting, and by dissolving the two interfaces, they end up, that's what it looks like when the two pillows are kind of nestled against each other, the two sand grains. And if you pull these apart and you look at the low stress places, you can see evidence for quartz precipitating on the surface. So here is what would have been a low stress grain contact. The water that dissolved all this quartz seeped into a low stress contact and started depositing quartz. And this is a great mechanism for cementing a rock, turning a sediment into a rock. It's also a great mechanism for changing the shape of the rock over pretty respectively medium amounts of time. It's not something that you can do overnight, but it is something that you could do substantially if you have millions of grains. You could change the shape of the rock a lot over the period of even weeks or years. You can have pretty big strains from this mechanism. A couple of funny things about chemistry, not my forte, but there's been a lot of experiments looking at the role of micas and clays that are near grains of quartz and feldspar. And because of the charge on the surface of micas and clays, they actually accelerate this process. They increase the solubility of quartz and feldspar in pore water. So if you have a dirty sandstone, you can have more strain in the same amount of time by solution creep than if you have a clean sandstone, which is kind of cool. What else do I want to say about this? Oh, so when we were in the first couple of weeks, when Laurent was talking about deformation mechanisms, we talked about the specific quartz microstructure that we see that's characteristic of different crystal plastic deformation mechanisms. With solution creep, the characteristic microstructures that we see are often things like changes in shape of grains. So if you're starting with a low-grade sedimentary rock and you know what the shape of the grains should be like, then you can infer that this process is taking place when you see these anomalies. As you go up in temperature and metamorphic grade, then the fabric that the rock takes on is not just controlled by one mechanism anymore. It's controlled by the combination of all the deformation mechanisms and all the different minerals that are affected, and by the mineral reactions that are going on during prograde metamorphism. So in a rock that can deform by, say, dislocation creep, the fabrics that we see are often dominated by characteristic fabrics associated with dislocation creep. That doesn't mean that solution creep is not going on. And in fact, in the same rocks, like the mylonites you looked at, you often see things like quartz veins popping up in pressure shadows. That quartz didn't come out of nowhere. It came out of solution. It came out of dissolution along the grain boundaries in the actively deforming mylonite and migrated to the low stress areas. So all the way down in the crust, this is still an important mechanism that's going on. And the more overprinting structural fabrics that we have, the harder it is to resolve how important is this role, how much strain is being taken up by this mechanism as opposed to the others. The crystalloplastic mechanisms that Laurent taught about, we have laws. We understand how they work. They're theoretically derived. We know what the rate and the viscosity and the velocity should be for those laws. For solution creep, we have laws that describe the very simplest of systems. But the more complex it gets, in other words, the closer we get to talking about a real rock, the more we can actually constrain things like what is the surface area of all the pore spaces between 5 and 10 kilometers depth in the San Andreas Fault? Like that's just like a non-starter sort of number. we could do it if we had a six-pack. We could sit around and we could make some calculations. But as a result, it's really hard to back out from first principles what rate of creep, for example, in a big crustal fault might be accommodated by this mechanism. But we know that it dominates a lot of the fabrics that we see in the rocks from these conditions. So here's an example from a recent paper. So these are from some sediments that were recovered from the SAFOD project. This is the San Andreas Fault Observatory at Depth, where they drilled down next to the San Andreas Fault and then they cut over and they cut through the fault zone. And they didn't find any rocks that they were expecting to find. They found all kinds of different stuff. And they cut through a creeping section of the fault, so their hole got cut off, like quite soon after getting through the fault. But they recovered a bunch of stuff. And so there's been, I don't know, many years of picking it apart to figure out what did they actually come away with. So I just pulled one figure from this paper. It's kind of interesting. So this is, this is a map that somebody made by basically mapping a bunch of different elements and then deciding which element distribution correlated to which minerals. So they've turned this into a mineral map from what was probably like an SEM map. And what we have here is these bands of chlorite, which is a relatively insoluble mineral that seem to be cutting off even things like this big quartz grain here, and maybe things like this K feldspar grain. So this is interpreted as a solution surface where water moving in the surface has collected silica and K feldspar in solution and moved it away. And as it reached chlorite grains, it couldn't dissolve them, so they're still there and they're just piling up at the surface, and probably also with some oxides that also show up here, little oxides in there and in there. So these bands represent kind of a net decrease in the amount of quartz and feldspar in the rock, and a proportional then increase in the percentage which is made up of insoluble minerals, chlorite, and oxides. So what they've done here is, this is what their map looks like right now. I don't know if that's exactly the same map, but it should be about the same thing. So they've got all this background rock, metasediment, and they've got these dark seams that they have interpreted as these solution seams. So what they've done is try to figure out how much volume is actually lost from the rock along these seams. And in order to do that, they've made some assumptions about things like the grain shape or the original composition of the rock, how much silica is missing. And so they're backing this out and kind of trying to reverse it like you would restore a cross section when you undo one structure after another. And they've come up with an interpretation that this rock in its initial undeformed state, before all this volume loss, would have been about 3 times bigger than it is now. And they, in this particular paper, they interpret this as they use this as a strain estimate to say how much strain on the San Andreas Fault in the creeping section is actually taken up by solution creep. And three times, like the rock is 3 times smaller than it ought to be. That seems like a massive volume loss, but it's actually pretty consistent with what we see if you just even look at a slate belt that has a strong slaty cleavage, which is also made in this very same way. If you look at the original mudstone, you get something like a depletion in quartz of 60 or 70% of the quartz is missing by the time you get to a slate. And the only place it could have gone is out in solution. So if you reprecipitate the dissolved minerals in the same part of the rock where you collected them from, you won't have a net quartz loss. But if you're flowing water through the rock and it's dissolving stuff and then it's moving on to another place, it'll leave a quartz vein in another rock, maybe on the other side of the fault in a granite, you'll find a quartz vein later. Where did that quartz come from? It was sucked out of these shales on the one side of the fault. So is that a lot of strain? Well, we don't really know how much time it represents, so it's hard to say. But overall, it looks like a lot of strain. Okay, so those are the major deformation mechanisms that we want to talk about in the seismogenic zone. So what are we going to call these rocks? We have a problem with fault rock classification in the seismogenic zone. So here's Rick Simpson again. This is 1977. It's one of the earlier papers that tried to put names on fault-related rocks and did it in a way that we kind of still use. There were previous attempts, but most of them have gone out of fashion by now. So this is from the Outer Hebrides fault zones, which are, I think, some islands that are off northern Scotland. And he's written a series of epic papers about these because this was like his actual PhD area. And everyone tells me that if you actually go there, it's too foggy to see the faults. Still, it's on the bucket list. So these faults are cutting granitic rocks. And it looks like these faults were active toward the base of the seismogenic zone where you're starting to get a lot of quartz and feldspar plasticity, but it's probably not hot enough that the crystallplastic deformation was able to keep up with the imposed deformation rate, whatever the plate rate was. So you have a combination of brittle and ductile behavior here. So these ones might look familiar already. We have, in the left-hand column, we have the myelinite series. So here's something that kind of looks like a granite still. You can see these are all cross-polarized photomicrographs, and I don't know what the scale is, but let's assume that he did the right thing and published all these photos at the same scale. So scale bars on them. So in the proto-myelinite, you can still see evidence of the original kind of grains of the granite. Maybe you can see that there's some either zonation or something, or undulose extinction that's getting stretched out, and you're starting to get a fabric to the rock, but you can still see the original granite. We have a myelinite, which has some porphyroclasts, some really fine-grained stuff, bands, and some coarser grain bands. And then we have an ultramyelinite where most of the ground mass here is really, really fine-grained and well-mixed. And so that's basically your ductile side of the equation. And then on the brittle side here, we have what he calls a proto-cataclysite. So this harkens back to kind of cataplastic flow, breaking and displacing of grains. Again, you can still see the distribution of quartz and feldspars, probably correlating to the original rock. If you advance that to cataclysite, then you're kind of starting to get dominated by fracture features and oxides and other things that are probably moving around with solution creep. And you have a lot of really fine material that's been ground up. Ultracataclysite, all you have is that really fine-grained stuff. Your mineralogy may have changed substantially from your original rock just by weathering and alteration. But this series of rocks is cohesive. And in the early kind of fault rock deformation or fault rock classification series, they made a big deal about whether something was cohesive or incohesive. So if it's cohesive, it's hard, it's lithified, they call it cataclysite. And if it's not, they call it a gouge or a breccia. If you could stick a shovel into it or a chisel and pick it apart grain by grain, if it's friable, they call it a breccia or a gouge. I don't actually think the distinction between cohesive and incohesive is that important. But at that time, they thought incohesive rocks formed shallow and if you were deeper, say 100 degrees or 200 degrees, then your brittle rocks would be cohesive and you'd be in the cataclysite series. I actually think that what controls the cohesiveness of the rock might have more to do with things like post-deformation cementation than it does with how the rock formed. Or a lot of the rocks that you collect at the surface are pretty weathered, and so they tend to be more friable. It doesn't mean that it didn't form as an ultracataclysite. So I'm not sure that that's a really useful way to think about it anymore. But there hasn't been a lot of improvements on this scheme. So one of the other things I have on my bucket list is to go back and look at, okay, these designations, the distinction between these different rocks has to do with grain size, grain shape, grain size distribution, matrix proportion, and process. So some of that is observational and some of it is interpreted. But what's missing from this entire scheme is this sneaky mechanism of solution creep. Here it is. It's affecting every grain and every rock in this entire zone of the crust, and it doesn't play any role in our existing fault rock classification system. So one of the things I'd like to work on in the future is come up with a scheme that's fully descriptive and then can correlate to an interpretive scheme that includes the role for solution creep in making these rocks. So it's, some people want to go skydiving or something, but I have much more boring goals for my life. Okay. Okay, and so now, oh, it's 3:30. Okay, I'm going to wrap this up real quick. Now we're going to talk briefly about the deformation mechanisms that occur only at very high slip rates. This is the dynamic weakening mechanisms. And first I'm going to explain why we shouldn't even need to talk about this. And that is because of this plot, this is a compilation published by DeToro et al. In Nature in 2011, where each color on here represents a different rock. We have the friction coefficient on the y-axis, and the x-axis here is actually sort of an energy term that he's come up with. And the reason why he's doing it that way is because it's a proxy for slip rate. You can think of it as slip rate, but for the same slip rate, you have a different amount of energy dumped into the surface if you're at higher stress. So he's normalizing for stress here and coming up with the energy term. So the thing to notice is that it doesn't matter what rock type you're in. He uses rocks where you don't really have earthquakes, like gypsum, anhydrite, ones where you do, dolomite, gabbro, novaculite, that's just a fancy word for a very specific type of chert. Clays, serpentine, marble, doesn't matter. Every rock, as you go to a higher energy density, meaning a higher slip rate, will go from whatever its initial friction was, whether it was super high or Byerly, or if it was a weak rock originally and it had like the clay stones here, they all go down to these low values as you dump more and more energy to the system. So the long and short of this plot is, doesn't matter what kind of rock it is. If you're in an earthquake, the slip will run away. You're going to be in the velocity weakening, fast slip conditions. Oops. Okay, so here's how that looks a little bit more spread out. We have the coefficient of friction. And now you can see how all these different rocks are behaving. So this is power density again. So it's just a proxy for slip rate, where this is fast. Fast. Eh. Okay, so these are seismic slip conditions where he's got the red box here. So all of these slow rocks here were sort of in Byerly friction, 0.7-ish values. And so these are for, let's see, those green ones are the carbonates. There's some quartz, and there's some granites. And all of the rocks, once you get up into this seismic-like energy density, they all drop in the coefficient of friction. But the other thing that's coded on this plot is what he thinks the reason for that drop in friction is. What is the deformation mechanism that acts in those rocks? So for this quartz experiments, you can see they start out at relatively high friction values, and then they come down and they end up at these very low friction values. And that is interpreted as gel lubrication causes that in quartz. If we look at the carbonates, the green diamonds, they also start out low velocity, high friction, and they come all the way down here, very low. And the mechanism for explaining that in carbonates is nanoparticle lubrication and decarbonation. Okay, then in some other rock types, gabbro, tonalite, monzodiorite, peridotite, so hard crystalline igneous rocks, all of this lubrication or drop in strength is attributed to melt lubrication, the formation of pseudotachylytes. For clays, here, clays and gypsum. The clays and gypsum stay strong all the way up into these like relatively high slip rates, and then they start dropping. Here they are. I'm sorry, these slides are going to be a mess later. And the mechanism for explaining those is flash heating, dehydration, and nanoparticle lubrication. So in this case, gypsum is not a sheet silicate, so it doesn't have any of the properties of sheet silicates, but what it does have is it contains volatiles, sulfates. So if you heat it up, you can drive off a gas. And that's the same as the clays, they contain hydroxyl groups. So if you heat it up, you can drive off the water. And then same thing with anhydrite, flash heating and nanoparticle lubrication down here. So it doesn't matter what your rock type is in detail, in an aggregate, you're going to get this weakening. But in detail, the reasons for explaining the weakening are going to be different for every single rock. So that's weird. It's not very elegant. We'll just say that. It's not very elegant. It's a new result. It's something we've only come to understand in the past 10 years that this is the case because this is the time period over which we've done a substantial number of high velocity friction experiments. But okay, so now I'm just going to walk you through a couple of photos of what would be, if these high velocity deformation mechanisms occur, what do they actually look like? So this is a fault where we think silica gel lubrication has occurred. By dropping the word gel, I'll explain why in a minute. So the mechanism is that when you shear a rock that's very rich in quartz, that you see the formation of this surface. This is the Corona Fault in San Francisco. It's cutting a block of chert. So the wall rock is chert. It's basically solid quartz. You see on the surface this layer of semi-transparent quartz. I want to call it goop or something, but it's hard. It's solid quartz. Here's what it looks like close up. You put your nose up to this outcrop. And the surface of it is so shiny that you can literally see your reflection in it. It's a super shiny fault. I don't know why. Yeah, okay. So here's what that stuff looks like in thin section. We have, let's see, I'm gonna go for it again. There's a thin section across the fault zone. So you have this kind of quartzy gouge here where you see lots of particles of chert. And then when you get to that slip surface, it's this kind of murky, fluidy looking stuff, very, very fine grained. So you can't actually see the individual grains in this matrix here. We zoom in a little bit more. We can see that each of this is a class of the wall rock chert, and it's got this nice mantle on it. It's picked up some kind of, it's like a snowball. It's picked up some kind of mantle of this really fine grained stuff from the matrix. So this is something we saw in the field, and we've now reproduced it in the lab. So going to try to figure out what this stuff is. So this is a cross section through a laboratory experiment where we had, this is a block of chert, this is a block of chert, and we just sheared them in a rotary shear apparatus. So they went round relative to one another, and then we cut a cross section through the fault. And so this is what this looks like in the experimental fault. And if we open this up and look at the surface of one of these kind of sharp through-going principal slip zones, if you will, that go through there, this is what it looks like on the surface. There are tiny nanoparticles, all of this junk you can see, and then there are these squished out smooth plates, also made of silica, that are like very polished and smooth and striated and show the slip direction. So this looks a little bit like one of those slippery days in the snow here, where you have the snow is kind of piled up and you could slip on it, and if you slipped on it, you might leave a heel track. It looks something like one of these. You might do that because you were compressing and smearing the snow together, and I think that's basically what happened here. in this stuff. When we get down and look at it in TEM, these individual particles here are actually amorphous silica. They don't have any crystalline structure whatsoever. We still get some little quartz grains in them. But when we ran these experiments, we saw that decay in frictional strength. It started out at like 0.5, 0.6, and when this material was produced in the fault, the coefficient of friction dropped to 0.1. So we think what happens in quartz is that the really high stresses that you get at the particle interfaces causes the crystal structure in the quartz to break down and produce this amorphous silica, which then basically has no strength. So it's like putting some squishy gumballs in your ball bearings, and then they kind of smear out and squish and roll and create a lubricant for the fault zone, which is kind of cool, and it only happens at high slip velocities. Okay, here's another one. This is for carbonates. So this beautiful image is from a Cristiano Colatini paper, and this is from a natural fault in Italy. And this is a calcite grain in the gouge. And when you get near the fault zone, you get this kind of porous texture in the calcite grains. And this is actually decarbonation texture. You'll see the same thing if you put calcite in a kiln and bring it up above a temperature of about 830 degrees. That temperature is where the calcite starts to break down into CaO and CO2. And the CO2 escapes. And so you're left with this lime calcium oxide mess, which is quite porous, and the CO2 is actually lost. Now, as you might imagine, at 830 degrees, the CO2 might be under a lot of pressure. It's a very hot gas. It's supercritical. And if it's mixing with supercritical water in the fault, you can generate a lot of pore pressure that way. So a couple of these field photos are showing what we think happens when you decarbonate the gouge in the fault zone and all of a sudden produce a whole bunch of gas into the pore space, is that you can actually drive a lot of particulate flow, pressurized particulate flow. So you get things like here, this is a little dike of gouge that's shooting across the myelinite in the footwall of a big thrust fault. And this is a place where the gouge is pressurized and started to inject and intrude into the fractured hanging wall or the damage zone of the fault, and is actually invading and pulling apart the breccias or the fractured rock to form a breccia that would have made the hanging wall. And in this particular case, this is from the Nalco thrust in Namibia. And if you go a couple meters off the fault, you find these big vugs filled with beautiful calcite crystals, really big crystals that are rhombohedral, and like it's really fun to take them out and smash them because then they make like 5,000 little rhombohedral crystals. But I think that's where the CO2 went. So that gives us an idea of how long it took for the CO2 to like cool down and then start to build new crystals out of the pore water. Kind of cool. Okay. This is, I'm going to skip this one. This one's a little bit too esoteric. Okay, so final thoughts about particulate flow. This is from Melange zone in Alaska, which is a subduction thrust fault that I think was active in the roughly Eocene, Paleocene, Eocene. So all of this rock was deformed by particulate flow. And what you can see here is that there is something, this is actually sandstone here. And the matrix here is kind of a black mudstone with chunks of sandstone in it. Of course, it's easier. Okay, but it looks like, if you follow the shape of it here, it looks like almost a snowball garnet or something. It's got this beautiful spiral form that speaks about a continuum deformation. Right? You can already see the sense of rotation here, and you can assign a shear sense to the system, and you can see that as the sandstone was rotating, these tails were spalling off into the matrix, and it gives you a real sense of continuum deformation. All of this was accomplished by particulate flow. So this kind of emphasizes the difficulty in understanding what the slip rate is because it's so coherent and the strain is so coherent. it seems like that might more likely be a slow slip event, but it's found in a fault. And in fact, here we have broken up pieces of pseudotachylyte all over the place. So we know that there were earthquakes cutting this fault as well. And so this is kind of, I don't know, this is one of my humility rocks where I look at it and I'm like, oh, I don't know shit about how these systems work. So it's good to have some of those in your collection. I don't really have a message for that, but. Okay, so the wrap-up slide. This is Simpson 83 diagram, which I've shown you to do due diligence, but luckily his students updated it, and obviously they also learned how to use Adobe Illustrator along the way. So this is a summary diagram that shows everything you need to know about the San Andreas Fault or a vertical fault cutting continental crust from the geologic features, oops, here, that we've talked about. Diagenesis, clay-rich gouge at the shallow layers going down to about 150 degrees, which in a continental fault like the San Andreas would put you at about 6 kilometers. Then we get into the seismogenic zone here, where they've drawn it down to about 300 degrees. Pseudotachylyte, which we'll talk about in the next section. Sub-green schist metamorphism, as we saw in the metamorphic diagram, and cataclysite. And here we have frictional faulting with dissolution, precipitation, creep as the major deformation mechanisms. And then above 300 degrees, or whatever appropriate threshold for the mineralogy of your rock, you get down, you start to see the tailing off of earthquakes. These are sort of the last or deepest earthquakes. And you start to spread out into myelinite zone that might get thicker than the shallow fault. And you start to see crystalloplastic deformation mechanisms become important. In this column, they talk about the frictional behavior. So we talked about stable or velocity strengthening behavior, which is, I didn't give you the equation, but that's when A minus B is positive. Here it's negative, so you're unstable. This is where you have stick slip behavior and earthquake stuff. So we have the shallow portion, which is stable and likes to creep. We have a deeper portion, which is stable and likes to creep. And then we have these kind of fun conditional zones, which produce all kinds of other weird behaviors. And then that kind of corresponds to the strength profile. So where frictional faulting is dominant, we have linear shear stress equals normal stress times friction kind of strength. Where you start to get the crystalloplastic deformation, you have the power law creep. And in between, you might have an area that's dominated by solution creep, and that kind of describes your deformation in that system. So this is the massive summary diagram for understanding the shallow part of fault zones. And this is as redrawn by Firing and Toy, 2011. All right. Okay, that's the bibliography for everything I just spoke about. So if you want to look up more, you can find it somewhere in this list. Yeah. So, okay. That's it for the lectures. Do you guys want to take a break before I introduce the problem set, or do you want to just carry on?
Queens, vote for carrying on.
2 minutes? No. All right.
Yeah, I'm fine with carrying on.
All right. You guys all right with that? Okay. All right, we're carrying on. Screen. Okay. Oh, sorry, I gotta open my file. Okay. Okay. All right, so we made it through faulting in the brittle regime. Now I'll just do a quick introduction to the lab. Oh, let me just fix this figure. There we go. Okay, starting again. Okay. Okay, so this has been alluded to a couple times in this lab, but frictional sliding produces heat. You know that because you rub your hands together to keep them warm. So that's, yeah, frictional sliding produces heat. You're doing work against friction when you rub something together, and that work turns into heat. So there have been a lot of arguments in the past about how much heat is produced and when. So we know if we rub our hands together quickly, we're going to get a lot of heat fast. If the fault is creeping slowly, it's also going to produce a little bit of heat. And how much is sort of a matter of debate. But heat anomalies on earthquake faults were inferred a long time ago, just from theoretical constraints and from the existence of pseudotachylyte. And with the advent of some recent awesome fault zone drilling in places where they've had a recent earthquake that has substantial slip at a relatively shallow depth, we've been able to drill to those faults and actually measure heat anomalies on the faults after the earthquakes. So here's an example from the 1999 Chi earthquake from Taiwan. The fault was a big reverse fault, so they were able to get it by drilling down through the hanging wall and hitting it at a respectable depth where there was enough slip on the fault that it generated a good heat anomaly. And so here's the positive thermal anomaly that was measured for a magnitude 7.5 earthquake, where the slip was about 10 meters in a right-reverse sense. And so if we wanted to know when that stress drops, the dynamic stress drop that we see during the earthquake, what is the stress at its lowest point, we can actually measure this, because if you know how much the fault slipped, and you know the thermal properties of the rock, you can figure out how much heat should be produced in that sliding. And that depends on the friction coefficient. So if you measure the heat, you can back calculate for the friction coefficient. And if you know the normal stress load on the fault, then you can calculate the shear stress. Okay? I said that backwards. But okay. So here's all the equations written out in words. Shear stress is a function of the cohesion plus normal stress times the friction coefficient. That is the Coulomb failure criteria, so that probably looks familiar. And the temperature change on the fault surface is a function of the shear stress times the displacement divided by, obviously not tensity. Dang, I'm just gonna fix it here. Density. There we go. Real-time slide repair. I can't blame that one on autocorrect. Okay. Temperature change on the fault is shear stress times displacement of the earthquake divided by the heat capacity times the density times the thickness of the fault. So these equations appear in your problem set. What you're going to do in the problem set is look at some earthquake slip surfaces where the heat production during slip was high enough to actually cause melting. So the temperature change here would be calculated as the temperature at which the fault rock melted minus the ambient temperature of the fault. So if the fault was active at a temperature of 200 degrees and the rock melted at 1,000 degrees, then the temperature change here would be 800 degrees. So what you're going to do is look at these thin sections of melted fault rock, pseudotachylyte, and you will be able to measure their thickness from the thin section. Heat capacity, I've given you a couple sources for the heat capacity of different rocks. So you can, and once you determine what kind of rock type you're dealing with, you can pick an appropriate value for the heat capacity for that. Same thing with density. We're just going to use the approximate rock type that you have to determine the density. The displacement is going to be a complete unknown because I don't know it, so I can't give it to you. So this is your unknown. Displacement of faults is like weirdly hard to measure, in fact. Especially if you know that fault probably had like 5 million earthquakes on it and you're looking for what was the slip in one of those earthquakes. The shear stress we know how to calculate. We can use this equation if we have a reasonable estimate for the friction coefficient and the normal stress on the fault. clear sketches. Okay. So this is from Rick Simpson again. And this is from, where's this paper? I covered it up. Anyway, 74. Oh yeah, okay, you can see it on there. So Simpson 74, what he did, he recognized something that was like quite handy, which is that when you're in the near surface environment, which he's extended to include the entire brittle zone apparently, the vertical stress is going to be one of your principal stresses. And that's because the Earth's surface is a free surface and you can't have shear stress resolved along it. So at the Earth's surface, the vertical stress is one of the principal stresses. So that vertical stress, but it could be your maximum or it could be your minimum principal stress. You don't necessarily know which one it is. But if you're in a normal faulting regime, then Andersonian theory says that your vertical stress is the strongest. It's driving the shortening. And you're in an extensional regime. So the horizontal stress is going to be your sigma 3, your minimum principal stress. Thrust is the opposite. Your horizontal principal stress is the maximum and the vertical stress is the minimum. So that same value of vertical stress, which would be the same at the same depth, will actually be your minimum stress. So the stresses are higher in a thrust system for the same depth than they are in a normal fault system. And for a strike-slip fault, the vertical principal stress is the intermediate principal stress. So the overall values of the stress that it's driven by the depth for the tectonic load is intermediate for a strike-slip system. So luckily I am able to tell you for every one of the pseudotachylyte samples whether they came from a thrust fault, a strike-slip fault, or a normal fault. So using Simpson's approximation and a reasonable estimate of the depth of faulting, which I've also given you, you can calculate what the normal stress on that fault should be. And by making a reasonable assumption about the coefficient of friction, you can go ahead and calculate shear stress on the fault. So now, if we go back to the previous slide, now everything is constrained except for the displacement in the earthquake, which we cannot observe. But it means that you can solve for that. Okay, so I thought I would give you a couple of examples of places where these faults come from. So these are 3 faults that I have studied, some of which are actually none of these 3 photos comes from the place that your samples come from, but they are similar. Okay, so this one is from the Pasagshak Point thrust. It's a subduction thrust in Alaska. And this black rock cutting through the middle here is a pseudotachylyte, but it's a very class-rich pseudotachylyte, so it's only about 5 to 10% melt. And it's mixed up with all kinds of grains from the wall rock and fault gouge grains. And you can see what the effect of that is because this was an earthquake slip surface that basically ruptured through a unconsolidated gouge that was still undergoing particle flow. So that particulate flow actually took some of this melty rock, and you can see after the earthquake melted this rock, you've got all these little wisps going into the wall rock, which is kind of amazing. Showing that there's like active deformation in the fault and in the wall rock during and after the slip. Pretty cool. This one here is from the Santa Rosa Myelinite zone in Southern California. And this is a beautiful tonalite. It's kind of your ideal environment for finding pseudotachylytes because the rock is white and the melt is black. This is the worst way to find pseudotachylytes. I've, in fact, worked at this outcrop for like 2 months, and then I came back the next year, and there was one sunny day, and then I found these pseudotachylytes. Like 2 months, I didn't see them because it was black rock and it was wet. But these ones are easy to find. They're gorgeous. And the interesting thing I wanted to point out here, for especially when you're thinking about some of the samples that you're going to be looking at, is that the actual fault surface is this super thin line coming through here. That is the fault surface. This is also a fault surface that intersects that. Maybe this one is too. There's a network of faults here. If you had this photo close up, you could look and you would see, for example, that the tonalite on this side has a different texture than the tonalite on this side. So we know there's been some displacement along the surface. But the contrast is that the pseudotachylyte is not living in the fault surface that made it. The pseudotachylyte is flowing into every little fracture and joint that intersects that fault surface. That's because when the earthquake is actually sliding, the fault surface is basically a free surface, and you have immediately after sliding, you have a high normal stress resolved perpendicular to that surface, and so all of the melt is pushed out into more fractures that are oriented more favorably for opening mode displacement. So it's very, very common to see a super thin fault, all the melt sucked off it. So if you see this in your thin sections that you're looking at, then and you use the thickness of the pseudotachylyte that's quenched in the fault surface, you're going to see a very tiny thickness. This is going to underestimate that thickness parameter that you need for the equation. It's going to say only a tiny amount of melt was produced, but you can see visibly that more than a tiny amount was produced. So if you see this and you want to estimate whatever the produced thickness of melt is, you want to incorporate somehow a volume estimate of this other stuff that's off the fault now. It's in these other tensile features or injected veins. This bottom image is just crazy beautiful. It's so confusing. It's so this is actually from the Fort Foster brittle zone, which is in Maine on the coast. This is actually from one of the students here is working on this for her master's. And this is a pseudotachylyte that was formed by two faults rupturing in parallel at one time. So we have one down here, cutting off the myelinite. We have one up here, cutting off that myelinite. And there are big blocks of wall rock that are caught up in the pseudotachylyte all the way along here. So this is actually interpreted as a big step over, a handoff between two segments of a fault. They're only a few centimeters apart. But in the intervening zone, there was some dilation. So lots of the melt that was produced along these fault strands pulled into the dilational zone during during the earthquake, or at least within the time frame that it took that melt to quench, which was probably seconds to minutes after the earthquake. So this is a big body of melt. It's bigger than a thin section. None of you will see something like this in thin section. But I just wanted to put in as a counterexample to this one up here, which has these very thin faults, that sometimes you have these very thick accumulations of melt too, and those two things are kind of complementary to each other. Okay. Really acing it with the misspellings on these. You can tell I made these slides this morning instead of last night. Let's just fix that. Altered pseudotachylytes. Great. Embarrassing. Okay. So pseudotachylytes is a tiny little film of melt, forms on the fault surface. If it quenches fast enough, it makes something glassy. If it takes a little bit longer to quench, or if it's particularly wet in the melt, it may never make a glass. It may basically form a microcrystalline ground mass, just like an igneous rock would at different quenching rates, kind of same range of textures. But either way, these things are super fine grained, maybe even amorphous. They don't really survive long in a geologic environment. If our seismogenic zone where these are formed is varying between 150 and 350 degrees and has a ton of fluids moving through it as appropriate as the most permeable part of the middle crust, then water is going to react with these materials. They're in a fault, so they're going to be deformed continuously during the healing and reloading process of the fault. They really shouldn't survive in the rock record at all. So there's a lot of papers out there that argue that pseudotachylytes are only rarely produced during earthquakes. And I say we don't have the rock record to make that claim, nor should we expect to have it, because they fundamentally preserve very poorly and should not be preserved in the rock record. So we are lucky when we find them. But I just wanted to show an example of one of the ways that the pseudotachylytes are lost from the rock record. So this is from a 2013 paper in the Journal of Structural Geology called Disappearing Ink, how pseudotachylytes are lost from the rock record. And the disappearing ink is like a little joke about how, like the Earth did write it down, but now it's disappeared and we can't actually read it. So, sorry, this lecture's getting really long. Sorry. Nope. Where's my pointer? Sorry. Can't see it. All right. So image A in the upper left-hand corner is a plain polarized scan of the whole slide. The bottom half, we have foliated tonalite. So this is a kind of the fault zone rock and the tonalite with some solution fabrics in it. Going through the middle, the kind of grassy green stuff and then the dark brown stuff, that is 2 layers of pseudotachylyte, 2 generations of pseudotachylyte. P1, the dark brown stuff that's above, is an older layer, and that's cut by P2. And there's remnants of P1 above and below, and then P2 cutting through the middle. And then above that, layer C is the cataclysite layer. And everything in here is green because this rock started life as a tonalite. It's mostly plagioclase. A little bit of water plus plagioclase is a great way to make epidote. So the tonalite wall rock, the cataclysite, and the pseudotachylyte are overwhelmingly replaced with epidote. So all these other photomicrographs around it are kind of showing the details of these little features. So if we look down first at C, that's cataclysite. It's got broken pieces of the primary rock-forming minerals from the tonalite. It's quartz, it's feldspar, it's angular, and the more you zoom down, the more tinier, more angular shards you get. That's a perfect cataclysite. It's formed by mineral grain breakage and particulate flow. Then in figure D, you can tell I turned the slide upside down because all the scale bars are like written upside down. We have this broken up tonalite on the bottom with really weathered and altered feldspars in it, and you can see that this old pseudotachylyte P1 has injected in lots of different little pokey places. It's picked up some clasts from the tonalite, and it's got a bit of a rough edge on it. And then there's a sharp boundary to P2. So P2 was the pseudotachylyte from the second earthquake that ruptured through the first earthquake surface. So it's a cross-cutting relation we're looking at there in the P1, P2 contact. And the difference texturally between P1 and P2, you can see that they have a different kind of clast population in terms of size and number of clasts, and they also have a different kind of color to the matrix here. And P2, it's a little bit coarser grained, and I can say that because there's a little bit more light coming through. This is a cross-polarized image, but P1 is really fine grained. It's quenched against the wall rock, so it probably quenched faster, and it's really fine. And then in P2, there's a little bit of coarsening, so you can actually see a little more of the matrix. Then the last 2 photos here, B and E, are from within the P2 layer. The P2 layer has 2 colors. It has a brown and a green color. And this is something we really commonly see in pseudotachylates because they melt along the wall rock, but they don't have long enough as a melt to homogenize. So we see compositional banding in the pseudotachylites that relates to the source of the melt in the wall rock. So if this is a tonalite, then the fault is cutting through feldspars, quartz, maybe some biotite, and a little bit of hornblende. A hornblende or a biotite is going to give you a really iron, magnesium, and water-rich melt, and it's going to have a different viscosity than the quartz or feldspar melt that's coming from the grain next door. So if those 2 melts don't have time to mix completely, you're going to end up with 2 melts of different viscosities flowing together next to each other, and that causes instabilities in the flow, and that causes little things like tiny folds that you can see in the P1 layer. That brown and green colors that are folded together in layers represent a more mafic melt and a more felsic melt. And after the pseudotachylyte quenched, it was sitting in the wall rock or sitting in the fault there for 10 years, 10,000 years, who knows. That plagioclase-rich matrix produced epidote. So we have 2 different melts. We have the original structure that shows that, and then we also have the altered colors that are reflecting the different composition and the propensity to alter to epidote eventually. So the reason why I went through this detailed explanation is because some of these features are going to show up in some of your slides. And you can use this especially to think about when you're going back and measuring the thickness of the melt, if you lump P1 and P2, you're going to get one bigger earthquake in terms of heat production than if you separate P1 and P2 and you say two smaller earthquakes affected this particular fall. Okay. So this is an example of what your slides are going to look like. This is actually a published photo of a slide from one of the localities. No, I didn't think I gave you this locality. This one's from the granites, but this is what your slides are going to look like. This is a kind of a simplest case. So this is from the high Sierra Nevada. It's got one beautiful vein running through it. And your decision as the geologist here would be to determine A, is this a single event? Is this a single slip pseudotachylyte vein, or do you see cross-cutting relations that might imply more than one earthquake here? 2, the thickness of this particular vein varies by 100% or more. What value for thickness is going to be representative on the scale of your thin section? Let's not reach outside the data that we have here, but check that out. 3, what are the minerals of this wall rock? So I'm going to there's some example problems that kind of walk you into the theory here when I say just assume that melting occurs at 1,000 degrees. But in fact, a rock is made of many different minerals, each with their own melting points. And the faster you want to melt something, you're going to get different melting points. So I referred you actually to a paper by John Spray, who studies impact pseudotachylytes. And he has calibrated the temperature of melt for different minerals at impact-like rates. Those are the melting temperatures you're going to use. So you'll want to identify the, using things like the mineralogy of the wall rock sample and the, maybe some thermal estimates from things like quartz microstructure that you're already familiar with from your earlier labs to guess at the temperature at which deformation occurred in the rock and what would the melt temperature have been for this rock at this rate. Yeah, so here's a really long list of papers, all of which are cited in the problem set. I think some of these, I direct you explicitly to use them. So that would be the Now et al. 2014, which gives you the temperature dependence of the rock properties. It would be Simpson 74, which will help you calculate the normal stress in the fault. Spray 2010, which tells you the melting temperatures at shock conditions. All the Simpson papers, which are basically, everyone should read all those. And other things are just sources that I use putting together the problem set. So I think there's really only 3 or maybe 4 papers, and you might have to reference a figure or a table in each of those papers to do it. But I guess, what I'll do is I'll just upload these papers. Does anyone have access to these papers, or should I upload them to the course site? I'll just upload them. We'll just make it easy. So I'll put them in later tonight so you can grab them. And I think that's it. Any questions? No questions?
No.
Okay.
Got it,
When you
Queen.
start working on the problem set, if you have any questions, feel free to email me.
Thank you, Christie.
Okay. Okay, signing off.